Welcome to Study Loop.
So we know the magnification for this situation, m, is equal to 0.2. For part A, it wants us to figure out what type of mirror we are dealing with. So the magnification is positive, which means the image is upright, of course. The positive magnification also shows that the image formed is a virtual image and the image distance from the mirror is negative. So the value of magnitude is positive and less than unity, or less than 1. So this shows the mirror is convex. So a positive magnification with a value that's less than 1 is a convex mirror. So you can write down that justification if you want to, but the solution here is convex. And we can box it in as our solution for part A. Part B wants to know the focal length of that. Well, you can tell from the image here that the focal length f is equal to 30, but convex mirrors always have a negative focal length. So the focal length f is equal to negative 30. And the units here are centimeters. And we can box it in as our solution for B. Part C wants us to calculate the radius of curvature for the mirror using the focal length. So it's equal to 2 times f. So 2 times f is equal to negative 60 centimeters. This can be boxed in as our solution for C. Part D wants us to figure out the distance from the image to the mirror. So to do that, we can use the thin lens equation, which says that 1 over the distance to the image, or excuse me, the distance to the object, p, divided by, or plus 1 over the distance to the image, I, is equal to 1 over the distance to the focal length, f. And p is what we're trying to find here. So the question is, how can we do that if we don't know I? But we do know I indirectly from our definition of magnification. I'll write it at top. M is equal to negative I over P. So you could replace I with negative MP. So what we have here is 1 over the focal length F is equal to 1 over P still, minus 1 over MP from that negative sign. So it'd be minus 1 over MP. We just replaced I with negative M times P. Okay, so now we can solve this for P. We find that P is equal to F times the magnification minus F all divided by the magnification. So plugging in the values for F and the value for magnification, we find that this is equal to 120 centimeters, which we can box in as our solution for part D. Part E wants us to find the distance to the image. So now we can go back to this equation here, which I'm pointing out with an arrow, to find the distance to the image and solve for I. This is E. We find that I is equal to P times F divided by P minus F. So plugging in our values for P and F, we find that I is equal to negative 24 centimeters. Part F says what's the magnification, but we knew that from the get-go, so we can just simply repeat that. Magnification M is equal to 0.2. G wants to know if the image that is formed is real or virtual. So to do that, we can just look at the sign of the value for the distance to the image, I, and since that is negative, it's a virtual image. So we can say, since I is negative, the image is virtual. And we can go ahead and box virtual in as the solution to G. Part H wants to know if the image that is formed is upright or inverted. So to answer that, we just have to look at the sign of the value for the magnification, which is positive. So since M is positive, the image is upright. And we can box in upright as our solution to H. And then the very last part, part I, wants to know if the image that is formed is on the same side or the opposite side as the object that formed it. But since the image is virtual, it is on the opposite. side. So we can just box in opposite as our solution to part I. So a virtual image for a lens, the image is on the same side, but a virtual image for a mirror, the image